Lesson 113 is about direct and inverse variation. Let's go ahead and start by talking about direct variation. And a good way to understand direct variation is to think of a gas like air. And for example, if you had a balloon, and this balloon was sitting in your room, and it was at some initial volume, we'll call that V1, and some initial temperature, T1, and then you started to heat your room up, you turned the heater on, and so now you have a different temperature, volume, and a different temperature, we'll call them V2 and T2. And it would just so happen that the balloon would expand, it would get bigger because the temperature increased if T2 was higher than T1. Now it just so happens for a gas like air, there's a ratio or a proportion, the ratio of the volume to the temperature always stays the same. And so that's called a direct variation, because both quantities that are involved in that relationship change in the same direction. They would either both change positively, so you'd have positive over positive, or they would both change negatively, so it would be negative over negative. The proportion or the ratio between them stays constant, and we could just say that it equals K, some constant value. Now if you've read this lesson 113, I'm explaining it a little bit different than the lesson. I think this is a better way to explain it, because eventually if you do chemistry class, you're going to have to know this relationship like this, and it's good to understand that a direct variation is a fraction like that. You write it like a fraction. Now for an inverse variation, you can probably understand what that means if you know what a direct variation is. A direct variation means as one quantity increases, the other increases, or the other way around. If one decreases, the other decreases. They both change in the same direction. Inverse variation, they change in opposite directions. An example of that can be seen with gases as well, such as air. If you had a balloon at an initial volume and pressure, we'll call those V1 and P1, then you increased the pressure. Let's say P2 was increased. Let me redraw that balloon, because V2 would actually decrease. If you increase the pressure surrounding that balloon, V2, that would decrease. That's what an inverse variation is. As one goes up, the other goes down. But that quantity, if you did those two factors multiplied together, P1 times V1, it stays constant. P1 V1 would equal P2 V2 equals some constant value K. As one goes up, the other goes down to keep that constant the same. So that's how an inverse variation works. As one goes up, the other goes down. That's why you multiply them together, because the factors multiplied together, that constant value, it stays the same or stays constant. The product of the two stays constant. Direct variation, the ratio of the two stays constant. One goes up, the other goes up. That's why you write direct variations as fractions, because if you wrote them as factors of each other, then as one went up, the other went up, you wouldn't have a constant value. You'd get bigger and bigger, or smaller and smaller if they kept decreasing. Likewise, with an inverse variation, if you wrote that as a fraction, as one went up, the other went down, your fraction would get either bigger or smaller depending on the change that you were doing. So when you're dealing with a pair of relationships that are fairly similar like this, a direct and inverse, a good thing to do is to memorize one of them really good. Like memorize that a direct variation is always written as a fraction. If you could remember that really good, then kind of by default you'll remember an inverse, our variation, is factors multiplied by each other. So try to remember that a direct variation is a ratio. Then by default you can remember inverse are factors. Let's do a practice problem. This problem says that the volume of a gas varied directly with the temperature. If the volume of a gas was 5 liters at a temperature of 280 Kelvin, what was the volume when the temperature was 840 Kelvin? Well, we know that this relationship here is a direct relationship because it says the volume varied directly with the temperature. So let's just set up a ratio V1 over T1 because we know when it varies directly we have to write it like a fraction. That ratio stays constant. So V1 over T1 is equal to V2 over T2. And we have three values that they've given us, a volume and two temperatures. We need that third volume. So we can solve for that. Let's just substitute in now. We have 5 liters for an initial volume and an initial temperature of 280 Kelvin is what that is. It's K for Kelvin. That's a temperature unit that's used in chemistry. And then V2, that is what we're trying to figure out. So we just write V2 there, and then I'll put 840 here. Now we could cross multiply to solve for this, but a problem like this, when we have the unknown on the top, it's just easier to multiply both sides by that denominator and get rid of that. And so then we have 840 times 5 over 280. And 840 over 280, that simplifies to 3 over 1. And so we end up with 3 times 5 is 15. So our new volume, V2, is equal to 15 liters. And I'll just put a cursive L there. That's an abbreviation for liters. So we saw that that was a direct relationship, and that told us right away how to set the problem up. Let's do another practice problem. This one says, under certain conditions, the pressure varies inversely with the volume. When the pressure is 70 atmospheres, the volume is 12 liters. What is the volume when the pressure is 15 atmospheres? So we want to figure out the volume when the pressure is 15 atmospheres. They gave us a pressure and volume combination of 70 and 12, and we were told that the pressure varies inversely with the volume. So that means we multiply those two quantities together, and so we'll say P1 V1, that's a constant which we could set equal to P2 times V2. And so as one increases, the other goes down, or vice versa. In this case, our pressure goes down, so we should expect our volume to go up. So we'll have, for an initial pressure, 70 atmospheres, or ATM. ATM is an abbreviation for atmospheres. That's just a unit for pressure. And then the volume initially was 12, so we have 70 times 12 is equal to P2, which is 15 atmospheres. So that pressure went down, so we should expect our volume to increase. Now let's divide both sides by 15. And if we do the math on that, we'll end up with 70 times 12 divided by 15 is equal to 56 liters. So V2 is equal to 56 liters. And so it did increase. And so that helps us, if we understand what an inverse relationship is, we guessed beforehand that our volume would increase because of what we know about an inverse relationship. So that helps us check our work and make sure we did the problem right. Indeed, our volume did increase. It's 56 liters. It started at 12. So here's a math relationship that has an immediate direct impact. This type of problem is used in chemistry. And I mean, what if you had a container that was only 20 liters in size? You could use an equation like this to figure out if you could even get down to 15 atmospheres of pressure, or would that make your container explode? So if you had an external pressure of 15 atmospheres with that initial pressure and volume combination, and your container only held 20 liters, then it might explode because that volume at 15 ATM is 56 liters. So scientists and chemists use this equation every day to help them understand gas relationships with pressure and volume. Okay, well that's all for lesson 113.